One of the challenges that we often have, even when we're flying vehicles like this, is that the planners that we design are hard to solve in real time. And so real time is, for an aerospace vehicle, is, about 10 hertz, quite fast. So that doesn't give you much computation time. And so you have the challenges of processing all the data. You have the vision data coming in, the laser data coming in. So you process that, then you got to make decisions about what to do. There's an optimization that you're running. So you're getting all these optimizers running in something close to tens of milliseconds. And so the question is, how do you do all that on a computer that you can fit on board? And so we always get looking for better and better computers, and still looking for better computers. But there's always a limit in terms of computation time. So one of the things we've been looking at recently is to basically create neural network versions of what these optimizers are. So you don't run the optimizer in real time. What you actually do is learn from the optimizer offline. So you run the optimizer thousands, if not millions of times offline, embed all of that knowledge into a neural net that basically just learns and becomes a student from an expert. And then you fly the student. And the student isn't running an optimizer, it's just basically running a neural net. The information comes in, the neural net is making the same decisions, hopefully, that the expert would have made, the optimizer, but it does it in like 1/10, if not 1/100th the amount of time. And then you get the information, the decisions come out the other side. So one of the things we've been doing is thinking about how to take that, not just on these vehicles, but actually working with one of the professors in the EE department, Kevin Chen. He turns out to be the twin brother of one of my previous grad students. And so I knew of Kevin's work when he was up in Harvard. He moved here. He's now created this very small UAV called the Softfly. It's only about 5 or 6 centimeters long. And so one of the things we showed last summer was we can take the algorithms we fly on big UAVs like this and do the exact same learning process and then fly them on these really small vehicles in Kevin's lab. And so that's working out really well. And so we do that for, essentially, any problem. Well, in fact, most of the problems we write down are too hard to solve in real time. And so what we do is we now do a lot of these learning exercises and then fly the learned neural nets instead. The main reason for going that route was just computation time. We just, it was a case of writing down problems that we just, it's like you write the problem down and go, well, this is what we want to solve, this is what we need. On the other hand, we couldn't solve it fast enough with the computers we had. And so on big machines like the one sitting behind me, you can probably solve them in real time, but you can't fly those. And so if you want to fly them on a machine, like you take a UAV, put a computer on it, it's going to be limited, plus it's got a lot of things it has to do. So the computation time was the real driver for getting down to, again, we were looking for reductions of about 1,000 in terms of like 1/1000th of the computation time to get it down to the point where it could now make fast decisions about the information coming in. And that's what led us to have to go this route. Because the challenge that typically comes up with any learning algorithm like this is, are there any gaps in what you've learned? So the next question becomes one of certification. Can you actually tell me? So you have an expert that, if I pose the problem to an expert and gave it enough time, pretty much guarantee is going to give me an answer. The student, on the other hand, is only learned from a finite number of expert tests. And so the concern always is one of, has the student learned enough from the expert to know what the answer is? And so that's when you have to have another step in the process, which is try to certify what the student has learned and see whether or not there's any gaps in their knowledge. It'd be the equivalent of giving like a final exam on the end of the semester. It's like you have the things you learned, demonstrated capabilities in homeworks and midterms, but at the end of the day, you give it a final exam and say, okay, well, how well did you actually pick up on this knowledge? And that's essentially what we want to do with the things that our students are learning before we put them out into the vehicles and actually fly them themselves.